Class 11, Unit 5, States of Matter. The snowflake falls, yet lays not long. Its feathery grasp on Mother Earth, ere sun returns it to the vapors whence it came, or to waters tumbling down the rocky slope. Objectives. After studying this unit, you will be able to explain the existence of different states of matter in terms of balance between intermolecular forces and thermal energy of particles, explain the laws governing behavior of ideal gases, apply gas laws in various real life situations, explain the behavior of real gases, describe the conditions required for liquefaction of gases, realize that there is continuity in gaseous and liquid state, differentiate between gaseous state and vapors, explain properties of liquids in terms of intermolecular attractions. Introduction. In previous units, we have learnt about the properties related to single particle of matter, such as atomic size, ionization enthalpy, electronic charge density, molecular shape and polarity, etc. Most of the observable characteristics of chemical systems with which we are familiar represent bulk properties of matter, that is, the properties associated with the collection of a large number of atoms, ions, or molecules. For example, an individual molecule of a liquid does not boil but the bulk boils. Collection of water molecules have wetting properties. Individual molecules do not wet. Water can exist as ice, which is a solid. It can exist as liquid, or it can exist in the gaseous state as water vapor or steam. Physical properties of ice, water, and steam are very different. In all the three states of water, chemical composition of water remains the same, that is H2O. Characteristics of the three states of water depend on the energies of molecules and on the manner in which water molecules aggregate. Same is true for other substances also. Chemical properties of a substance do not change with the change of its physical state, but rate of chemical reactions do depend upon the physical state. Many times in calculations, while dealing with data of experiments, we require knowledge of the state of matter. Therefore, it becomes necessary for a chemist to know the physical laws which governs the behavior of matter in different states. In this unit, we will learn more about these three physical states of matter, particularly liquid and gaseous states. To begin with, it is necessary to understand the nature of intermolecular forces, molecular interactions, and effect of thermal energy on the motion of particles, because the balance between these determines the state of a substance. Intermolecular forces. Intermolecular forces are the forces of attraction and repulsion between interacting particles, atoms, or molecules. This term do not include the electrostatic forces that exist between the two oppositely charged ions and the forces that hold atoms of a molecule together, that is covalent bonds. Attractive intermolecular forces are known as van der Waals forces in honor of Dutch scientist Johannes van der Waals 1837 to 1923, who explained the deviation of real gases from the ideal behavior through these forces. We will learn about this later in this unit. Van der Waals forces vary considerably in magnitude and include dispersion forces or London forces, dipole-dipole forces, and dipole-induced dipole forces. A particularly strong type of dipole-dipole interaction is hydrogen bonding. Only a few elements can participate in hydrogen bond formation, therefore, it is treated as a separate category. We have already learnt about this interaction in Unit 4. At this point, it is important to note that attractive forces between an ion and a dipole are known as ion dipole forces, and these are not van der Waals forces. We will now learn about different types of van der Waals forces. Dispersion forces or London forces. Atoms and nonpolar molecules are electrically symmetrical and have no dipole moment because their electronic charge cloud is symmetrically distributed. But a dipole may develop momentarily even in such atoms and molecules. This can be understood as follows. Suppose we have two atoms A and B in the close vicinity of each other, figure 5.1a. It may so happen that momentarily electronic charge distribution in one of the atoms, say A, becomes unsymmetrical, that is, the charge cloud is more on one side than the other, figure 5.1b and c. This results in the development of instantaneous dipole on the atom A for a very short time. This instantaneous or transient dipole distorts the electron density of the other atom B, which is close to it, and as a consequence, a dipole is induced in the atom B. The temporary dipoles of atom A and B attract each other. Similarly, temporary dipoles are induced in molecules also. This force of attraction was first proposed by German physicist Ritz London, and for this reason force of attraction between two temporary dipoles is known as London forces. Another name for this force is dispersion force. These forces are always attractive and interaction energy is inversely proportional to the sixth power of the distance between two interacting particles, that is 1 upon r raised to power 6, where r is the distance between two particles. These forces are important only at short distances, about 500 picometer, and their magnitude depends on the polarizability of the particle. Dipole-dipole forces. Dipole-dipole forces act between the molecules possessing permanent dipole. Ends of the dipole possesses partial charges, and these charges are shown by Greek letter delta. Partial charges are always less than the unit electronic charge 1.610 in raised to power minus 19 coulomb. The polar molecules interact with neighboring molecules. Figure 5.2a shows electron cloud distribution in the dipole of hydrogen chloride, and figure 5.2b shows dipole-dipole interaction between two HCl molecules. This interaction is stronger than the London forces but is weaker than ion-ion interaction because only partial charges are involved. The attractive force decreases with the increase of distance between the dipoles. As in the above case, here also the interaction energy is inversely proportional to the distance between polar molecules. Dipole-dipole interaction energy between stationary polar molecules, as in solids, is proportional to 1 divided by r raised to power 3, and that between rotating polar molecules is proportional to 1 divided by r raised to power 6, where r is the distance between the polar molecules. Beside dipole-dipole interaction, polar molecules can interact by London forces also. Thus, cumulative effect is that the total of intermolecular forces in polar molecules increase. Dipole-induced dipole forces. This type of attractive forces operate between the polar molecules having permanent dipole and the molecules lacking permanent dipole. Permanent dipole of the polar molecule induces dipole on the electrically neutral molecule by deforming its electronic cloud, figure 5.3. Thus, an induced dipole is developed in another molecule. In this case also, interaction energy is proportional to 1 divided by r raised to power 6, where r is the distance between two molecules. Induced dipole moment depends upon the dipole moment present in the permanent dipole and the polarizability of the electrically neutral molecule. We have already learnt in Unit 4 that molecules of larger size can be easily polarized. High polarizability increases the strength of attractive interactions. In this case also, cumulative effect of dispersion forces and dipole-induced dipole interactions exist. Hydrogen bond. As already mentioned in section 5.1, this is special case of dipole-dipole interaction. We have already learned about this in Unit 4. This is found that the molecules in which highly polar NH, or HF bonds are present, although hydrogen bonding is regarded as being limited to N, O, and F, but species such as Cl negative may also participate in hydrogen bonding. Energy of hydrogen bond varies between 10 to 100 kilojoule mole inverse. This is quite a significant amount of energy. Therefore, hydrogen bonds are powerful force in determining the structure and properties of many compounds. For example, proteins and nucleic acids. Strength of the hydrogen bond is determined by the Coulombic interaction between the lone pairs of the electronegative atom of one molecule and the hydrogen atom of other molecule. Following diagram shows the formation of hydrogen bond. Intermolecular forces discussed so far are all attractive. Molecules also exert repulsive forces on one another. When two molecules are brought into close contact with each other, the repulsion between the electron clouds and that between the nuclei of two molecules comes into play. Magnitude of the repulsion rises very rapidly as the distance separating the molecules decreases. This is the reason that liquids and solids are hard to compress. In these states, molecules are already in close contact. Therefore, they resist further compression, as that would result in the increase of repulsive interactions. Thermal energy. Thermal energy is the energy of a body arising from motion of its atom or molecules. It is directly proportional to the temperature of the substance. It is the measure of average kinetic energy of the particles of the matter and is thus responsible for movement of particles. This movement of particles is called thermal motion. Intermolecular forces versus thermal interactions. We have already learned this that intermolecular forces tend to keep the molecules together, but thermal energy of the molecules tends to keep them apart. Three states of matter are the result of balance between intermolecular forces and the thermal energy of the molecules. When molecular interactions are very weak, molecules do not clinch together to make liquid or solids unless thermal energy is reduced by lowering the temperature. Gases do not liquefy on compression only. Although molecules come very close to each other and intermolecular forces operate to the maximum. However, when thermal energy of molecules is reduced by lowering the temperature, the gases can be very easily liquefied. Predominance of thermal energy and the molecular interaction energy of a substance in three states is depicted as follows. We have already learnt the cause for the existence of the three states of matter. Now we will learn more about gaseous and liquid states and the laws which govern the behavior of matter in these states. We shall deal with the solid state in class 12th. The gaseous state. This is the simplest state of matter. Throughout our life, we remain immersed in the ocean of air, which is a mixture of gases. We spend our life in the lowermost layer of the atmosphere called troposphere, which is held to the surface of the earth by gravitational force. The thin layer of atmosphere is vital to our life. It shields us from harmful radiations and contains substances like dioxygen, dinitrogen, carbon dioxide, water vapor, etc. Let us now focus our attention on the behavior of substances which exist in the gaseous state under normal conditions of temperature and pressure. A look at the periodic table shows that only 11 elements exist as gases under normal conditions. The gaseous state is characterized by the following physical properties. Gases are highly compressible. Gases exert pressure equally in all directions. Gases have much lower density than the solids and liquids. The volume and shape of gases are not fixed. These assume volume and shape of the container. Gases mix evenly and completely in all proportions without any mechanical aid. Simplicity of gases is due to the fact that the forces of interaction between their molecules are negligible. Their behavior is governed by same general laws, which were discovered as a result of their experimental studies. These laws are relationships between measurable properties of gases. Some of these properties, like pressure, volume, temperature, and mass, are very important because relationships between these variables describe stage of the gas. Independence of these variables leads to the formulation of gas laws. In the next section, we will learn about gas laws. The gas laws. The gas laws, which we will study now, are the result of research carried on for several centuries on the physical properties of gases. The first reliable measurement on properties of gases was made by Anglo-Irish scientist Robert Boyle in 1662. The law which he formulated is known as Boyle's law. Later on, attempts to fly in air with the help of hot air balloons motivated Jacques Charles and Joseph Louis Gay-Lussac to discover additional gas laws. Contribution from Avogadro and others provided lot of information about gaseous states. Boyle's law, pressure-volume relationship. On the basis of his experiments, Robert Boyle reached to the conclusion that at constant temperature, the pressure of a fixed amount, that is, number of molecules n of gas, varies inversely with its volume. This is known as Boyle's law. Mathematically, it can be written as P is inversely proportional to V at constant temperature and n, which implies that P is equal to K1 into 1 upon V, where K1 is proportionality constant. The value of constant K1 depends upon the amount of gas, temperature of the gas, and the units in which pressure and volume are expressed. On rearranging equation 5.2, we obtain PV is equal to K1. It means that at constant temperature, product of pressure and volume of a fixed amount of gas is constant. If a fixed amount of gas at constant temperature T occupying at pressure P1 undergoes expansion so that volume becomes V2 and pressure becomes P2, then according to Boyle's law, P1 V1 is equal to P2 V2 is equal to constant. Then P1 upon P2 is equal to V2 upon V1. Figure 5.5 shows two conventional ways of graphically presenting Boyle's law. Figure 5.5a is the graph of equation 5.3 at different temperatures. The value of K1 for each curve is different because for a given mass of gas, it varies only with temperature. Each curve corresponds to a different constant temperature and is known as an isotherm constant temperature plot. Higher curves correspond to higher temperature. It should be noted that volume of the gas doubles if pressure is halved. Table 5.1 gives effect of pressure on volume of 0.09 mole of CO2 at 300. Figure 5.5b represents the graph between P and 1 upon V. It is a straight line passing through origin. However, at high pressures, gases deviate from Boyle's law, and under such conditions, a straight line is not obtained in the graph. Experiments of Boyle's in a quantitative manner prove that gases are highly compressible because when a given mass of a gas is compressed, the same number of molecules occupy a smaller space. This means that gases become denser at high pressure. A relationship can be obtained between density and pressure of a gas by using Boyle's law. By definition, density D is related to the mass m and the volume V by the relation D is equal to m upon V. If we put value of V in this equation, from Boyle's law equation, we obtain the relationship D is equal to m upon k1 into p is equal to k dash into p. This shows that at a constant temperature, pressure is directly proportional to the density of a fixed mass of the gas. Problem 5.1. A balloon is filled with hydrogen at room temperature. It will burst if pressure exceeds 0.2 bar. If at 1 bar pressure of the gas occupies 2.27 liter volume, up to what volume can the balloon be expanded? Solution. According to Boyle's law, P1 V1 is equal to P2 V2. If P1 is 1 bar, V1 will be 2.27 liter. If P2 is equal to 0.2 bar, then V2 is equal to P1 V1 upon P2. V2 is equal to 1 bar into 2.27 liter upon 0.2 bar is equal to 11.35 liter. Since balloon bursts at zero point 0.2 bar pressure, the volume of balloon should be less than 11.35 liter. Charles' law, temperature volume relationship. Charles and Gay-Lussac performed several experiments on gases independently to improve upon hot air balloon technology. Their investigation showed that for a fixed mass of a gas at constant pressure, volume of a gas increases on increasing temperature and decreases on cooling. They found that for each degree rise in temperature, volume of a gas increases by 1 upon 273.15 of the original volume of the gas at 0 degree Celsius. Thus, if volume of gas at 0 degree Celsius and T degree Celsius are V0 and Vt respectively, then Vt is equal to V0 plus T upon 273.15 into V0, then implies that Vt is equal to V0 into 1 plus T upon 273.15, gives that Vt is equal to V0 into 273.15 plus T upon 273.15. At this stage, we define a new scale of temperature such that T degree Celsius on new scale is given by T is equal to 273.15 plus T, and 0 degree Celsius will be given by T naught is equal to 273.15. This new temperature scale is called the Kelvin temperature scale or absolute temperature scale. Thus, 0 degree Celsius on the Celsius scale is equal to 273.15 Kelvin at the absolute scale. Note that degree sign is not used while writing the temperature in absolute temperature scale, that is Kelvin scale. Kelvin scale of temperature is also called thermodynamic scale of temperature and is used in all scientific works. Thus, we add 273, more precisely 273.15 to the Celsius temperature to obtain temperature at Kelvin scale. If we write Tt is equal to 273.15 plus T and T naught is equal to 273.15. In the equation 5.6, we obtain the relationship Vt is equal to V naught into Tt upon T naught. Vt upon V naught is equal to Tt upon T naught. Thus, we can write a general equation as follows. V2 upon V1 is equal to T2 upon T1, gives that V1 upon T1 is equal to V2 upon T2, gives that V upon T is equal to constant is equal to K2. Thus, V is equal to K2 into T. The value of constant K2 is determined by the pressure of the gas, its amount, and the units in which volume V is expressed. Equation 5.10 is the mathematical expression for Charles' law, which states that pressure remaining constant, the volume of a fixed mass of a gas is directly proportional to its absolute temperature. Charles found that for all gases at any given pressure, graph of volume versus temperature in Celsius is a straight line and on extending to zero volume, each line intercepts the temperature axis at minus 273.15 degrees Celsius. Slopes of lines obtained at different pressure are different, but at zero volume all the lines meet the temperature axis at minus 273.15 degrees Celsius. Figure 5.6. Each line of the volume versus temperature graph is called isobar. Observations of Charles can be interpreted if we put the value of T in equation 5.6 as minus 273.15 degrees Celsius. We can see that the volume of the gas at minus 273.15 degrees Celsius will be zero. This means that gas will not exist. In fact, all the gases get liquefied before this temperature is reached. The lowest hypothetical or imaginary temperature at which gases are supposed to occupy zero volume is called absolute zero. All gases obey Charles' law at very low pressures and high temperatures. Problem 5.2. On a ship sailing in Pacific Ocean where temperature is 23.4 degrees Celsius, a balloon is filled with 2-liter air. What will be the volume of the balloon when the ship reaches Indian Ocean where temperature is 26.1 degrees Celsius? So V1 is equal to 2 liter, T1 is equal to 23.4 plus 273 Kelvin is equal to 296.4 Kelvin. T2 is equal to 26.1 plus 273 is equal to 299.1 Kelvin. From Charles' law, V1 upon T1 is equal to V2 upon T2 gives that V2 is equal to V1 T2 upon T1. V2 is equal to 2L into 299.1 Kelvin upon 296.4 Kelvin. It is equal to 2 liter into 1.009 is equal to 2.018 liter. Gay-Lussac's law, pressure temperature relationship. Pressure in well inflated tires of automobiles is almost constant, but on a hot summer day, this increases considerably and tire may burst if pressure is not adjusted properly. During winters, on a cold morning, one may find the pressure in the tires of a vehicle decreased considerably. The mathematical relationship between pressure and temperature was given by Joseph Gay-Lussac and is known as Gay-Lussac's law. It states that at constant volume, pressure of a fixed amount of a gas varies directly with the temperature. Mathematically, P is directly proportional to T. Gives that P upon T is equal to constant is equal to K3. This relationship can be derived from Boyle's law and Charles' law. Pressure versus temperature, Kelvin graph at constant molar volume is shown in figure 5.7. Each line of this graph is called isochore. Avogadro law, volume amount relationship. In 1811, Italian scientist Amedeo Avogadro tried to combine conclusions of Dalton's atomic theory and Gay-Lussac's law of combining volumes, Unit 1, which is now known as Avogadro law. It states that the equal volumes of all gases under the same conditions of temperature and pressure contain equal number of molecules. This means that as long as the temperature and pressure remain constant, the volume depends upon number of molecules of the gas, or in other words, amount of the gas. Mathematically, we can write V is directly proportional to N, where N is the number of moles of the gas. V is equal to K4 into N. The number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 raised to the power 23 and is known as Avogadro constant. You will find that this is the same number which we came across while discussing definition of a mole, unit 1. Since volume of gas is directly proportional to the number of moles, 1 mole of each gas at standard temperature and pressure STP will have same volume. Standard temperature and pressure means 273.15 Kelvin, 0 degrees Celsius temperature, and 1 bar, that is exactly 10 raised to the power 5 Pascal pressure. These values approximate freezing temperature of water and atmospheric pressure at sea level. At STP, molar volume of an ideal gas or a combination of ideal gases is 22.71098 liter mole inverse. Molar volume of some gases is given in table 5.2. Table 5.2, molar volume in liters per mole of some gases at 273.15 Kelvin and 1 bar. STP. Argon 22.37, carbon dioxide 22.54, dinitrogen 22.69, dioxygen 22.69, dihydrogen 22.72, ideal gas 22.71. Number of moles of a gas can be calculated as follows. N is equal to M upon capital M, where small m is equal to mass of the gas under investigation and capital M is equal to molar mass. Thus, V is equal to K4 into small m upon capital M. Equation 5.13 can be rearranged as follows. Capital M is equal to K4 into small m upon V is equal to K4 into D. Equation number 5.14. Here d is the density of the gas. We can conclude from equation 5.14 that the density of a gas is directly proportional to its molar mass. A gas that follows Boyle's law, Charles' law, and Avogadro's law strictly is called an ideal gas. Such a gas is hypothetical. It is assumed that intermolecular forces are not present between the molecules of an ideal gas. Real gases follow these laws only under certain specific conditions when forces of interaction are practically negligible. In all other situations, these deviate from ideal behavior. You will learn about the deviations later in this unit. Ideal gas equation. The three laws which we have learned till now can be combined together in a single equation which is known as ideal gas equation. At, at constant temperature and N, V is directly proportional to 1 upon P. Boyle's law. At constant P and N, V is directly proportional to T. Charles' law. At constant pressure and temperature, V is directly proportional to N. Avogadro law. Thus, V is directly proportional to the Nt upon V. V is equal to R into Nt upon V, where R is proportionality constant. On rearranging the equation 5.6, we obtain PV is equal to nRT, R is equal to PV upon Nt. R is called gas constant. It is same for all gases. Therefore, it is also known as universal gas constant. Equation 5.17 is called ideal gas equation. Equation 5.18 shows that the value of R depends upon units in which P, V and T are measured. If three variables in this equation are known, fourth can be calculated. From this equation, we can see that at constant temperature and pressure, n moles of any gas will have the same volume because V is equal to nRT upon P, and nRT and P are constant. This equation will be applicable to any gas. Under those conditions, when behavior of the gas approaches ideal behavior, volume of 1 mole of an ideal gas under STP conditions 273.15 Kelvin and 1 bar pressure is 22.710981 liter mole inverse. Value of R for 1 mole of an ideal gas can be calculated under these conditions as follows. R is equal to 10 raised to power 5 into R is equal to 10 raised to power 5 Pascal into 22.71 into 10 raised to power minus 3 meter cube upon 1 mole into 273.15 Kelvin is equal to 8.314 Pascal meter cube. Kelvin inverse mole inverse is equal to 8.314 into 10 raised to power minus 2 bar liter. Kelvin inverse mole inverse is equal to 8.314 joule Kelvin inverse mole inverse. At STP conditions used earlier, 0 degree Celsius and 1 atmospheric pressure, value of R is 8.20578 10 raised to power minus 2 later atm K inverse mole inverse. Ideal gas equation is a real relationship between four variables and it describes the state of any gas. Therefore, it is also called equation of state. Let us know now. Go back to the ideal gas equation. This is the relationship for the simultaneous variation of the variables. If temperature, volume and pressure of a fixed amount of gas vary from T1, V1 and P1 to T2, V2 and P2, then we can write P1 V1 upon T1 is equal to nR and P2 V2 upon T2 is equal to nR. Gives that P1 V1 upon T1 is equal to P2 V2 upon T2. Equation 5.19 is a very useful equation. If out of 6 values of 5 variables are known, the value of unknown variable can be calculated from the equation 5.19. This equation is also known as combined gas law. Problem 5.3. At 25 degrees Celsius and 760 millimeter of Hg pressure, a gas occupies 600 ml volume. What will be its pressure at a height where temperature is 10 degrees Celsius and volume of the gas is 640 milliliter? Solution. P1 is equal to 760 mm Hg, V1 is equal to 600 ml, T1 is equal to 25.273 is equal to 298 Kelvin. V2 is equal to 640 ml and T2 is equal to 10 plus 273 is equal to 283 Kelvin. According to combined gas law, P1 V1 upon T1 is equal to P2 V2 upon T2. P2 is equal to P1 V1 T2 upon T1 V2. P2 is equal to 760 mmHg into 600 ml into 283 Kelvin upon 640 ml into 298 Kelvin is equal to 676 mmHg. Density and molar mass of a gaseous substance. Ideal gas equation can be rearranged as follows. N upon V is equal to P upon RT. Replacing N by M upon capital M, we get small m upon capital M into V is equal to P upon RT. D upon capital M is equal to P upon RT, where D is the density. On rearranging equation 5.21, we get the relationship for calculating molar mass of a gas. M is equal to dRT upon P. Dalton's law of partial pressures. The law was formulated by Johann Dalton in 1801. It states that the total pressure exerted by a mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases, that is, the pressures which these gases would exert if they were enclosed separately in the same volume and under the same conditions of the temperature. In a mixture of gases, the pressure exerted by the individual gas is called partial pressure. Mathematically, P total is equal to P1 P plus P2 plus P3 plus and so on at constant temperature volume, where P total is the total pressure exerted by the mixture of gases and P1, P2 and P3 etc. are partial pressures of gases. Gases are generally collected over water and therefore are moist. Pressure of dry gas can be calculated by subtracting vapor pressure of water from the total pressure of the moist gas, which contains water vapors also. Pressure exerted by saturated water vapor is called equastension. Equastension of water at different temperatures is given in table 5.3. P dry gas is equal to P total minus equastension. Table 5.3. Equastension of water vapor pressure as a function of temperature. Temperature 273.15, pressure 0.0060, temperature 295.15, pressure 0.0260, temperature 283.15, pressure 0.0121, temperature 297.15, pressure 0.0295, 288.15, pressure 0.0168, temperature 299.15, pressure 0.0331, temperature 291.15, pressure 0.0204, temperature 301.15, pressure 0.0372, temperature 293.15, pressure 0.0230, temperature 303.15, pressure 0.0418. Partial pressure in terms of mole fraction. Suppose at temperature T, three gases enclosed in the volume V exert partial pressure P1, P2 and P3 respectively. Then P1 is equal to N1 RT upon V. P2 is equal to N2 RT upon V. P3 is equal to N3 RT upon V, where N1, N2, N3 are the number of moles of these gases. Thus, expression for total pressure will be P total is equal to P1 P plus P2 plus P3 is equal to N1 into RT upon V plus N2 into RT upon V plus N3 into RT upon V is equal to N1 plus N2 plus N3 into RT upon V. On dividing P1 by P total, we get P1 upon P total is equal to N1 upon N1 plus N2 plus N3 into RTV upon RTV is equal to N1 upon N1 plus N2 plus N3 is equal to N1 upon N is equal to X1, where N is equal to N1 plus N2 plus N3. X1 is called mole fraction of first gas. Thus, P1 is equal to X1 P total. Similarly, for other gases, we can write P2 is equal to X2 P total and P3 is equal to X3 P total. Thus, the general equation can be written as Pi is equal to Xi P total, where Pi and Xi are partial pressure and mole fraction of ith gas respectively. If total pressure of a mixture of gas is known, the equation 5.29 can be used to find out pressure exerted by individual gases. Problem 5.4. A neon dioxygen mixture contains 70.6 gram dioxygen and 167.5 gram neon. If pressure of the mixture of gases in the cylinder is 25 bar, what is the partial pressure of dioxygen and neon in the mixture? Number of moles of dioxygen is equal to 70.6 gram upon 32 gram mole inverse is equal to 2.21 mole. Number of moles of neon is equal to 167.5 gram upon 20 gram mole inverse is equal to 8.375 mole. Mole fraction of dioxygen is equal to 2.21 upon 2.21 plus 8.375 is equal to 2.21 upon 10.585 is equal to 0.21. Mole fraction of neon is equal to 8.375 upon 2.21 plus 8.375 is equal to 0.79. Alternatively, mole fraction of neon is equal to 1 minus 0.21 is equal to 0.79. Partial pressure of a gas is equal to mole fraction. Partial pressure of oxygen is equal to 0.2125 bar is equal to 5.25 bar. Partial pressure of neon is equal to 0.7925 bar is equal to 119.75 bar. Kinetic molecule theory of gases. So far we have learnt the laws, example Boyle's law, Charles' law, etc., which are concise statements of experimental facts observed in the laboratory by the scientists conducting careful experiments. Is an important aspect of scientific method, and it tells us how the particular system is behaving under different conditions. However, once the experimental facts are established, a scientist is curious to know why the system is behaving in that way. For example, gas laws help us to predict that pressure increases when we compress gases. But we would like to know what happens at molecular level when a gas is compressed. A theory is constructed to answer such questions. A theory is a model, that is a mental picture that enables us to better understand our observations. The theory that attempts to elucidate the behavior of gases is known as kinetic molecular theory. Assumptions or postulates of kinetic molecular theory of gases are given below. These postulates are related to atoms and molecules which cannot be seen. Hence, it is said to provide a microscopic model of gases. Gases consist of large number of identical particles, atoms of molecules that are so small and so far apart on the average that the actual volume of the molecules is negligible in comparison to the empty space between them. They are considered as point masses. This assumption explains the great compressibility of gases. There is no force of attraction between the particles of gas at ordinary temperature and pressure. The support for this assumption comes from the fact that gases expand and occupy all the space available to them. Particles of a gas are always in constant and random motion. If the particles were at rest, occupied fixed positions, then the gas would have a fixed shape, which is not observed. Particles of a gas moves in all possible directions in straight lines. During their random motion, they collide with each other and with the walls of the container. Pressure is exerted by the gas as a result of collision of the particles with the walls of container. Collisions of a gas molecules are perfectly elastic. This means that total energy of molecules before and after collision remains same. There may be exchange of energy between colliding molecules. Their individual energies may change, but the sum of their energies remain constant. If there were loss of kinetic energy, the motion of molecules will stop and gases will settle down. This is contrary to what is actually observed. At any particular time, different particles in the gas have different speeds and hence different kinetic energies. This assumption is reasonable because as the particles collide, we expect their speed to change. Even if initial speed if of all the particles was same, the molecular collisions will disrupt this uniformity. Consequently, the particles must have different speeds which go on changing constantly. It is possible to show that through the individual speeds are changing, the distribution of speeds remains constant at a particular temperature. If a molecule has variable speed, then it must have a variable kinetic energy. Under these circumstances, we can talk only about average kinetic energy. In kinetic theory, it is assumed that average kinetic energy of the gas molecule is directly proportional to the absolute temperature. It is seen that on heating a gas at constant volume, the pressure increases. On heating the gas, kinetic energy of the particles increases and these strike the walls of the container more frequently, thus exerting more pressure. Kinetic theory of gases allows us to derive theoretically all the gas laws studied in previous sections. Calculation and predictions based on kinetic theory of gases agree very well with the experimental observations and thus establish the correctness of this model. Behavior of real gases. Deviation from ideal gas behavior. Our theoretical model of gases corresponds very well with the experimental observations. Difficulty arises when we try to test how far the relation PV is equal to nRT reproduce actual pressure volume temperature relationship of gases. To test this point, we plot PV versus P plot of gases because at constant temperature PV will be constant, Boyle's law, and PV versus P graph at all pressures will be a straight line parallel to x-axis. Figure 5.8 shows such a plot constructed from the actual data for several gases at 273 Kelvin. It can be seen easily that at constant temperature, PV versus P plot for real gases is not a straight line. There is a significant deviation from ideal behavior. The two types of curves are seen. In the curves of dihydrogen and helium, as the pressure increases, the value of PV also increases. The second type of plot is seen in the case of other gases like carbon monoxide and methane. In these plots, first there is a negative deviation from ideal behavior. The PV value decreases with increase in pressure and reaches to a minimum value characteristic of a gas. After that, PV value starts increasing. The curve then crosses the line for ideal gas and after that shows positive deviation continuously. It is thus found that real gases do not follow ideal gas equation perfectly under all conditions. Deviation from ideal behavior also becomes apparent when pressure versus volume plot is drawn. The pressure versus volume plot of experimental data, real gases, and that theoretically calculated from Boyle's law, ideal gas should coincide. Figure 5.9 shows that these plots it is apparent that at very high pressure, the measured volume is more than the calculated volume. At low pressures, measured and calculated volumes approach each other. It is found that real gases do not follow Boyle's law, Charles' law, and Avogadro law perfectly under all conditions. Now, two questions arise. Why do gases deviate from the ideal behavior? Second, what are the conditions under which gases deviate from the ideality? We get the answer of the first question if we look into postulate of kinetic theory once again. We find that two assumptions of the kinetic theory do not hold good. These are A. There is no force of attraction between the molecules of gas. B. Volume of the molecules of a gas is negligibly small in comparison to the space occupied by the gas. If assumption A is correct, the gas will never liquefy. However, we know that gases do not liquefy when cooled and compressed. Also, liquids formed are very difficult to compress. This means that forces of repulsion are powerful enough and prevent squashing of molecules in tiny volume. If assumption B is correct, the pressure versus volume graph of experimental data, real gas, and that theoretically calculated from Boyle's law, ideal gas should coincide. Real gases show deviation from ideal gas law because molecules interact with each other. At high pressures, molecules of gases are very close to each other. Molecular interactions start operating. At high pressure, molecules do not strike the walls of the container with full impact because these are dragged back by other molecules due to molecular attractive forces. This affects the pressure exerted by the molecules on the walls of the container. Thus, the pressure exerted by the gas is lower than the pressure exerted by the ideal gas. P ideal is equal to P real plus An square upon V square. Observed correction pressure terms. Here A is a constant. Repulsive forces also become significant. Repulsive interactions are short range interactions and are significant when molecules are almost in contact. This is the situation as at high temperature, at a high pressure. The repulsive forces cause the molecules to behave as small but impenetrable spheres. The volume occupied by the molecules also becomes significant because instead of moving in volume V, they are now restricted to volume V minus NB, where NB is and where NB is approximately the total volume occupied by the molecules themselves. Here B is a constant having taken into account the corrections for pressure and volume. We can rewrite equation P plus An square upon V square into V minus Nb is equal to nRT. Equation 5.31 is known as van der Waals equation. In this equation, N is the number of moles of gases. Constant A and B are called van der Waals constant and their value depends on the characteristic of a gas. Value of A is measure of magnitude of intermolecular attractive forces within the gas and is independent of temperature and pressure. Also, at very low temperature, intermolecular forces become significant as the molecules travel with low average speed. These can be captured by one another due to attractive forces. Real gases show ideal behavior when conditions of temperature and pressure are such that the intermolecular forces are practically negligible. The real gases show ideal behavior when pressure approaches zero. The deviation from ideal behavior can be measured in terms of compressibility factor Z, which is the ratio of product PV and nRT mathematically. Z is equal to PV upon nRT. For ideal gas, Z is equal to 1 at all temperatures and pressures because PV is equal to nRT. The graph of Z versus P will be a straight line parallel to pressure axis. Figure 5.10. For gases which deviate from ideality, value of Z deviates from unity at very low pressures. All gases shown have Z equal to 1 and behaves an ideal gas. At high pressure, all the gases have Z greater than 1. These are more difficult to compress. At intermediate pressure, most gases have Z less than 1. Thus, gases show ideal behavior when the volume occupied is so large that the volume of the molecules can be neglected in comparison to it. In other words, the behavior of the gas becomes more ideal when pressure is very low. Up to what pressure a gas will follow the ideal gas law depends upon nature of the gas and its temperature. The temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called Boyle temperature or Boyle point. Boil point of a gas depends upon its nature. Above their boil point, real gases show positive deviations from ideality and Z values are greater than 1. The forces of attraction between the molecules are very feeble. Below boil temperature, real gases first show decrease in Z value with increasing pressure which reaches a minimum value. On further increase in pressure, the value of Z increases continuously. Above explanation shows that at low pressure and high temperature gases show ideal behavior. These conditions are different for different gases. More insight is obtained in the significance of Z if we note the following derivation. Z is equal to P into V real upon nRT. If the gas shows ideal behavior, then V ideal is equal to nRT upon P. On putting this value of nRT upon V in equation 5.33, we have Z is equal to V real upon V ideal. From equation 5.34, we can see that compressibility factor is the ratio of actual molar volume of a gas to the measured volume of it, if it were an ideal gas at temperature and pressure. In the following section, we will see that it is not possible to distinguish between gaseous state and liquid state, and that liquids may be considered as continuation of gas phase into a region of small volumes and very high molecular attraction. We will also see how we can use isotherms of gases for predicting the conditions for liquefaction of gases. Liquefaction of gases. First, complete data on pressure, volume, temperature relations of a substance in both gaseous and liquid state was obtained by Thomas and Drews on carbon dioxide. He plotted isotherms of carbon dioxide at various temperatures. Figure 5.11. Later on, it was found that real gases behave in the same manner as carbon dioxide. Andrews noticed that at high temperatures, isotherms look like that of an ideal gas, and the gas cannot be liquefied even at high pressure. As the temperature is lowered, shape of the curve changes and data shows considerable deviation from ideal behavior. At 30.98 degrees Celsius, carbon dioxide remains gas up to 73 atmospheric pressure. Point E in figure 5.11, at 73 atmospheric pressure, liquid carbon dioxide appears for the first time. The temperature 30.98 degrees Celsius is called critical temperature Tc of carbon dioxide. This is the highest temperature at which liquid carbon dioxide is observed. Above this temperature, it is gas. Volume of 1 mole of the gas at critical temperature is called critical volume Vc, and pressure at this temperature is called critical pressure Pc. The critical temperature, pressure and volume are called critical constants. Further, increase in pressure simply compresses the liquid carbon dioxide, and the curve represents the compressibility of the liquid. The steep line represents the isotherm of liquid. Even a slight compression results in steep rise in pressure, indicating very low compressibility of the liquid. Below 30.98 degrees Celsius, the behavior of the gas on compression is quite different. At 21.5 degrees Celsius, carbon dioxide remains as a gas only up to point B. At point B, liquid of a particular volume appears. Further compression do not change the pressure. Liquid and gaseous carbon dioxide coexist, and further application of pressure results in the condensation of more gas until the point C is reached. At point C, all the gas has been condensed, and further application of pressure merely compresses the liquid as shown by steep line. A slight compression from volume V2 to V3 results in steep rise in pressure from P2 to P3 5.11. Below 30.98 degrees Celsius critical temperature, each curve shows the similar trend. Only length of horizontal line increases at lower temperatures. At critical point, horizontal portion of the isotherm merges into one point. Thus, we see that a point like A in the figure 5.11 represents gaseous state, a point like D represents liquid state, and a point under the dome-shaped area represents existence of liquid and gaseous carbon monoxide in equilibrium. All the gases upon compression at constant temperature, isothermal compression, show the same behavior as shown by carbon dioxide. Also above discussion shows that gases should be cooled below their critical temperature for liquefaction. Critical temperature of a gas is highest temperature at which liquefaction of a gas first occurs. Liquefaction of so-called permanent gases, that is, gases which show continuous positive deviation in Z value, requires cooling as well as considerable compression. Compression brings the molecules in close vicinity, and cooling slows down the movement of molecules. Therefore, Intermolecular interaction may hold the closely and slowly moving molecules together and the gas liquefies. It is possible to change a gas into liquid or a liquid into gas by a process in which always a single phase is present. For example, in figure 5.11, we can move from point A to F vertically by increasing the temperature. Then we can reach the point G by compressing the gas at the constant temperature along this isotherm at 31.1 degrees Celsius. The pressure will increase. Now we can move vertically down towards D by lowering the temperature. As soon as we cross the point H on critical isotherm, we get liquid. We end up with liquid, but in this series of changes we do not pass through two phase region. If process is carried out at the critical temperature, substance always remains in one phase. Thus there is continuity between the gaseous and liquid state. The term fluid is used for either a liquid or a gas to recognize this continuity. Thus, the liquid can be viewed as a very dense gas. Liquid and gas can be distinguished only when the fluid is below its critical temperature and its pressure and volume lie under the dome. Since in that situation, liquid and gas are in equilibrium and a surface separating the two phases is visible. In the absence of this surface, there is no fundamental way of distinguishing between two states. At critical temperature, liquid passes into gaseous state imperceptibly and continuously. The surface separating two phases disappears. Section 5.10.1. A gas below the critical temperature can be liquefied by applying pressure and is called vapor of the substance. Carbon dioxide gas below its critical temperature is called carbon dioxide vapor. Critical constants for some common substances are given in table 5.4. Substance H2 temp TC PC VC 33.2 12.9 70.0650 HE 5.3 2.29 0.0577 N2 126 33.9 0.0900 O2 154.3 50.4 0.0744 CO2 304.10 73.9 0.0956 H2O 647.1 220.6 0.0450 NH3 405.5 113.0 0.0723. Problem 5.5. Gases possesses characteristics critical temperature which depends upon the magnitude of intermolecular forces between the gas particles. Critical temperatures of ammonia and carbon dioxide are 405.5 Kelvin and 304.10 Kelvin respectively. Which of these gases will liquefy first when you start cooling from 500 Kelvin to their critical temperature? Solution. Ammonia will liquefy first because its critical temperature will be reached first. Liquefaction of CO2 will require more cooling. Liquid state. Intermolecular forces are stronger in liquid state than in gaseous state. Molecules in liquids are so close that there is very little empty space between them, and under normal conditions, liquids are denser than gases. Molecules of liquids are held together by attractive intermolecular forces. Liquids have definite volume because molecules do not separate from each other. However, molecules of liquids can move past one another freely. Therefore, liquids can be poured and can assume the shape of the container in which these are sorted. In the following sections, we will look into some of the physical properties of the liquid such as vapor pressure, surface tension and viscosity. Vapor pressure. If an evacuated container is partially filled with liquid, a portion of liquid evaporates to fill the remaining volume of the container with vapor. Initially, the liquid evaporates and pressure exerted by vapors on the walls of the container, vapor pressure increases. After some time, it becomes constant, an equilibrium is established between liquid phase and vapor phase. Vapor pressure at this stage is known as equilibrium vapor pressure or saturated vapor pressure. Since process of vaporization is temperature dependent, the temperature must be mentioned while reporting the vapor pressure of a liquid. When a liquid is heated in an open vessel, the liquid vaporizes from the surface. At the temperature at which vapor pressure of the liquid becomes equal to the external pressure, vaporization can occur throughout the bulk of the liquid and vapors expand freely into the surroundings. The condition of free vaporization throughout the liquid is called boiling. The temperature at which vapor pressure of liquid is equal to the external pressure is called boiling temperature. At that pressure, vapor pressure of some common liquids at various temperature is given in figure 5.12. At 1 atm pressure, boiling temperature is called normal boiling point. If pressure is 1 bar, then the boiling point is called standard boiling point of the liquid. Standard boiling point of the liquid is slightly lower than the normal boiling point because 1 bar pressure is slightly less than 1 atmospheric pressure. The normal boiling point of water is 100 degrees Celsius, 373 Kelvin. Its standard boiling point is 99.6 degrees Celsius, 372.6 Kelvin. At high altitudes, atmospheric pressure is low. Therefore, liquids at high altitudes boil at low temperatures in comparison to that at sea level. Since water boils at low temperature on hills, the pressure cooker is used for cooking food in hospitals, surgical instruments are sterilized in autoclaves in which boiling point of water is increased by increasing the pressure above the atmospheric pressure by using a weight covering the vent. Boiling does not occur when liquid is heated in a closed vessel. On heating continuously, vapor pressure increases. At first, a clear boundary is visible between liquid and vapor phase because liquid is more dense than vapor. As the temperature increases more and more, molecules go to vapor phase and density of vapor rises. At the same time, the liquid becomes less dense. It expands because molecules move apart. When density of liquid and vapors becomes the same, the clear boundary between liquid and vapors disappear. This temperature is called critical temperature, about which we have already discussed in section 5.9. Surface tension. It is well known fact that liquids assume the shape of the container. Why? It is then small drops of mercury form spherical beads instead of spreading on the surface. Why do particles of soil at the bottom of river remain separated but they stick together when taken out? Why does a liquid rise or fall in a thin capillary as soon as the capillary touches the surface of the liquid? All these phenomena are caused due to characteristic property of liquids called surface tension. A molecule in the bulk of liquid experience equal intermolecular forces from all sides. The molecule therefore does not experience any net force. But for the molecule on the surface of liquid, net attractive force is towards the interior of the liquid. Figure 5.13 due to the molecules below it. Since there are no molecules above it, liquids tend to minimize their surface area. The molecules on the surface experience a net downward force and have more energy than the molecules in the bulk, which do not experience any net force. Therefore, liquids tend to have minimum number of molecules at the surface. If surface of the liquid is increased by pulling a molecule from the bulk, attractive forces will have to be overcome. This will require expenditure of energy. The energy required to increase the surface area of the liquid by 1 unit is defined as surface energy. Its dimensions are joule meter raised to power minus 2. Surface tension is defined as a force acting per unit length perpendicular to the line drawn on the surface of liquid. It is denoted by Greek letter gamma. It has dimensions of kilogram as raised to power minus 2 and in SI unit it is expressed as Newton meter inverse. The lowest energy state of the liquid will be when surface area is minimum. Spherical shape satisfies these conditions. That is why mercury drops are spherical in shape. This is the reason that sharp glasses edges are heated for making them smooth. On heating, the glass melts and the surface of the liquid tends to take the rounded shape at the edges, which makes the edges smooth. This is called fire polishing of glass. Liquids tend to rise or fall in capillary because of surface tension. Liquids wet the things because they spread across their surface at, as thin film. Moist soil grains are pulled together because surface area of thin film of water is reduced. It is surface tension which gives stretching property to the surface of a liquid. On flat surface, droplets are slightly flattened by the effect of gravity, but in the gravity free environments, drops are perfectly spherical. The magnitude of surface tension of a liquid depends on the attractive forces between the molecules. When the attractive forces are large, the surface tension is large. Increase in temperature increases the kinetic energy of the molecules, and the effectiveness of intermolecular attraction decreases. So, surface tension decreases as the temperature is raised. Viscosity. It is one of the characteristic properties of liquids. Viscosity is a measure of resistance to flow which arises due to the internal friction between layers of fluid as they slip past another while fluid flows. Strong intermolecular forces between molecules hold them together and resist movement of layers past one another. When a liquid flows over a fixed surface, the layer of molecules in the immediate contact of surface is stationary. The velocity of upper layers increases as the distance of layers from the fixed layers increases. This type of flow in which there is a regular gradation of velocity in passing from one layer to the next is called laminar flow. If we choose any layer in the flowing liquid, figure 5.14, the layer above it accelerates its flow and the layer below it retards its flow. If the velocity of a layer at a distance dz is changed by a value du, then velocity gradient is given by the amount du upon dz. A force is required to maintain the flow of layers. This force is proportional to the area of contact of layers and velocity gradient, that is F is directly proportional to A. A is the area of contact. F is directly proportional to du upon dz, where du upon dz is velocity gradient. The change in velocity with distance. F is directly proportional to A into du upon dz. Then F is equal to neta A du upon dz, where neta is proportionality constant and is called coefficient of viscosity. Viscosity coefficient is the force when velocity gradient is unity and the area of contact is unit area. Thus, neta is measure of viscosity. SI unit of viscosity coefficient is 1 Newton second per square meter is equal to Pascal second. In CGS system, the unit of coefficient of viscosity is poise, named after great scientist Jean-Louis Poiseuille. 1 poise is equal to 1 gram centimeter inverse S inverse is equal to 10 raised to power minus 1 kilogram meter inverse S inverse. Greater the viscosity, the more slowly the liquid flows. Hydrogen bonding and van der Waals forces are strong enough to cause high viscosity. Glass is an extremely viscous liquid. It is so viscous that many of its properties resembles solids. However, property of flow of glass can be experienced by measuring the thickness of window panes of old buildings. These become thicker at bottom than at the top. Viscosity of liquids decreases as the temperature rises because at high temperature molecules have high kinetic energy and can overcome the intermolecular forces to slip past one another between the layers.